Okay, once again, welcome to 16.3 Digital Communication. This is part 2. We will go to the lecture. After that, we will go to do some partial question. So basically, we are going to do transmitting analog signal in digital form and recovering the analog signal. Let's just review what we have done previously. We have an analog signal. The first step is to sample the signal at regular interval. That means read the graph at regular interval. We call it sampling rate. And we got the value at each particular time. And then each value we convert to voltage. And the signal voltage is then converted to digital. And then it's transmitted as a series of pulse. Then, right? Today's lecture will be using the electronic to do it. We have gone over how to convert from decimal to binary, and you should be able to convert from binary to decimal. So at least up to about 40 there. Can use calculator, can use calculation. That way, right? 2 to the power 0 is the first one. That is 1. And then 2 to the power 1 is the second one. That is 1. So it means that if we have 1, 1, then this is 2 plus 1 is 3. This one is 0. Right? 2 plus 1 is 3, and then this is 8. So 11. Okay, so that's how we get our value. Then ways in which reproduction of signal may be improved. Right? You look at, we can see that this part maybe correspond to that, but we have missed out the maximum, we have missed out the peak there. How to improve the signal? Increase the number of bits in the digital number at each sampling so that the height is reduced. You want to reduce this height, you want to jump too high. Then the next one is number 2. Increase the sampling frequency so that the depth or the width is reduced. Okay? You will miss out some of this point there. Some of this point there. Where these two are quite similar, but we will miss out this point, that point there, for the maximum. And then we said it's important that we have what we call Nyquist frequency. Fmax is the maximum frequency of the signal or information. And the theorem says for recovery, your sampling frequency must be twice the maximum frequency. Okay, so now we are going to look at transmission part of the analog signal in digital form. First, it can be your speech, your music, or your data. Right? Analog signal, that's where your input is. It passes through a bandpass filter, a device that passes frequency within a certain range and reject or attenuate frequency outside the range. Right? Remember, we have to sample at regular frequency, sample at regular rate. So this electronic analog signal must be regular sample. So the clock is the one to hold it and then send. Hold it, send. Right? Then we have to convert it from analog to digital. Read the voltage of the graph. Right? You sample it. So the sampling clock is the one that determines how fast we send the reading to the analog to digital converter. So here it's converted to digital. So if there are n bits, then we need n wires. So n wires at the digital to analog. So this will be in the form of pulse modulation. So analog voltage produce n-bit binary number. Then the digital to analog converter must have also n wires for each of the binary number. So we look at a construction filter. Construction filter is essentially a filter circuit that smooth out, right? That gets how to get this analog signal, smooth it out to something like that. Move out the step height from the DAC. It operates in such a way that it appears to guess. Yeah, just try to guess how the graph will look like or interpolate. And the value of analog signal between the sample. Right? Try to guess rather than give you all these steps there. Try to smooth it out and guess how the graph will look like. Sample and hold circuit. Repeatedly sample and stop for a brief period. The value of the analog voltage at some moment in time. Remember, the analog signal varies continuously with time. The rate at which such samples are taken is governed by the frequency of the sampling clock. That sampling clock determine, right? You read, pass, read, pass, out. Sampling rate, determine the sampling rate. Right? So the sampling clock controls the time at which the samples are taken. One advantage of using high-frequency clock is to enable high-frequency component in the signal to be detected. Okay, so that is a partial question. This is a block diagram. That's a figure 12.1. Represent a system for digital transmission of analog data. Describe the function of the analog to digital converter. Analog signal, right? It's analog signal is sampled at regular interval. The sample signal is converted into binary number. So that's the purpose of the ADC, to convert your analog signal to binary. And then multi-channel means wires are, if there are n bits and wires to the DAC. Such as, right, the transmission cable has a number of channels. Right? Remember, each channel is each wire, one wire. One channel is required for each bit of digital number. For short distance, this type of transmission with n wires is only for short distance, like from your computer to your printer. Parallel transmission of information between transmitter and receiver. Applies transmitter, applies to receiver. This means that n bits of codes are simultaneously sent down n separate wire. Each wire for 1 bit. So if there are n wires, it's for n bits. At a rate governed by the frequency of the sampling clock. This is the fastest and simplest method for digital signal transmission, but not viable when transmission over long distance. Right? So we can use it for short distance between computer and a printer. But long distance, we have a problem. Right? Long distance, not viable. Why? Each cable is going to cost money. So if there are n wires, you have to multiply by n times the cost. Right? Cost of long cable composed of n wires would be high. Right? Next term we are going to encounter is skew, oblique, slant, not parallel. So problem with parallel transmission over distance, transmitted signal would suffer from skew. That means each bit of the n bit word takes a slightly different time to travel along the individual wire. With parallel short distance, okay, they can reach the receiver at the same time, but long distance, they may not reach at the same time. As the cable becomes longer and longer, the effect worsens, and then the end bit received at any moment in time may not be the same as the end bits of original transmitted. So example is that's what we send 1111 pulse initially. After some distance, we will see, right? It's completely different. This is the fastest, this is the slowest. So we will probably get a 0, 1, 0, completely different from 1111. Okay, so that's the problem. How do we do it? And bits of code for the as our ADC, analog to digital converter, are input into an we use another electronic circuit known as parallel to serial register. The circuit swallows, take the entire n bit word on one clocking pulse, and then transmit it one bit at a time. Right? Take all the n bit, transmit it all one bit at a time under the control of another clock, another clocking pulse. So that's the transmission line. This n bit progress along the single conductor to the receiver. This part is the receiver, and it is in this single conductor that the digital signal exists. Exists in their pulse form. So the same thing, if we convert parallel to serial, now we have to convert the series back into parallel. Right? Serial to parallel converter. And then the same thing. This part is ADC, this part is DAC. Digital to analog converter. Discuss briefly the effect on society of the change to transmission of signal in digital rather than analog form. Now, what is the effect on society? Digital more reliable than analog. So of course we prefer to use digital. Fewer people employed in telephone industry. Previously, in the old way where we can only use one cable to make telephone call, you have to call the operator, and the operator is the one who connect for us to, if it's our station call, who we want to speak to, and we have really special allotted time. Fewer people. So now we don't need operator already. All the electronic will control for us. Greater multiplexing means reduced cost per call. So previously, one wire, one caller, and one receiver. So it becomes very expensive. Now, if we can have one cable, many people using it, then it becomes cheaper. Called multiplexing. We can use frequency multiplexing, right? Like frequency modulation. Reduced cost means available to more people. So if cost is less expensive, more people can use the telephone. Huge expansion international call. So at the same time, it's reduce cost, less expensive, and we can afford to make more overseas call. Not like it will cost a few $100 during my time just to make overseas call. Now it's cheaper than that. Huge expansion of non-voice communication. Right? Like our smartphone, right? We prefer to use texting message. Right? Instant texting message. That allow us development or expansion of internet, and also introduction of multi-channel cable TV company. We can see the effect on society of digital transmission. Okay, that's completed. Let's go to the worksheet now. You can find it in my note. Okay, study the sample above. The vertical line are sample taken as the original signal. We sample it at regular interval. You should be able to see from the graph what is the sampling period. Right? Sampling period, this is if 1, 2, 3, 4. So 2 millisecond divided by 4 will give you the period 0.5 millisecond. And from the period, we should be able to calculate our sampling rate. That means our sampling frequency 1 over the period. This millisecond is 10 to the power minus 3. So we get 2 kilohertz. Okay, let's try one of partial question. This 216, paper 41. Question 5 in the paper. The variation with time of the voltage level part of an analog signal is shown in figure 5.1. The signal is sampled at 0.25 millisecond. Each sample is converted into the 4-bit digital number. Okay, so let us see how to do that. First, you can draw a line there and then read the value 6. Right? That value is 6. And read another value. Yeah, told is 0.25 millisecond. So at 5, read again 8. Right? The first one is 11. About there, nearly halfway there. And this is at 0.75. It's about, usually we cannot round it off to 15 unless it's slightly more than 15. Digital is different from what we have learned in our maths. So 14 less than 15 is still 14. Then at 1, we just read a line at 1, then read a horizontal line, read that. It's about 5. And at 1.25, read that. It's about 3. And at 1.5, read that. It's about 1. Okay, so 14.8, as I say, we should read it as not 15, not like in maths. Right? Electronic is different. The circuit will just read for you 14. They don't know how to read 14.8 unless you have Mobits. Okay, so there are figure 5. Figure 5.2, the various time at which the voltage level is sampled. The digital number for time, this is given. Right? The question is 11. On figure 5.2, underline the most significant bits for the digital number at t equals 0. Most significant is just this one, the 1 here. Just underline it. Underline that. Then complete. We have done that. Right? We have analog, reading, convert it to digital. Okay, and it's just to help you. Right? This 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4. So if you want 6, 6 is 4 plus 2, so it's 1, 1, 0. Right? There's a 0 here. Or 8, 8 is here, 1, 0, 0. 14, 14 is basically this 8 plus 4 plus 2. So it's 1, 1, 1, 0. After transmission of the digital numbers, the signal is passed through a digital to analog converter. On figure 5.2, import the transmitted analog signal for the digital analog converter. So now we convert it back. I remember it's 11, 6, 8, 14, 5, 1. So 11, first one. And the next one is 6. Next one is 8. Remember, sampling time is 0.25. Next one is 14. And the next one is 5. There is 3. There is 1. So that's what we get. Right? That's the original signal. Right? You see that we missed this part up. Yeah. Okay. We have missed out. The transmitter signal in B has less detail than the analog signal in figure 5.1. Suggest and explain two means by which the level of detail in the transmitter signal could be increased. It's just remember that we have just done. Increase the sampling frequency. Means take more reading. Shorter time interval. So that will reduce the step width or depth. Number of bits. Increase number of bits. Increase number of bits in each number so that the step height is reduced. A digital signal is produced by sampling an analog signal and passing through an analog to digital converter. State what is meant by digital signal. Memory work. Series of high and low with no intermediate value. Only 1 and 0. High voltage, low voltage, or 0 voltage, no in between. State one change to the sampling or to the ADC that will improve the accuracy of the reproduction of the original analog signal. Okay, use higher sampling frequency or rate, or use more bit in each sample, or use more level in each sample, same thing. Right? More bit means more level in each sample. The least significant digit of a 4-bit digital number 1100 represent a signal voltage of 2.5. Determine the signal voltage in millivolt representing this digital number. Okay, can work it out. If you know this calculator, 1100, we start from 2 to the power 0, to the power 1, to the power 2, to the power 3. So this one is 4, this one is 8, so it's 14. Decimal is, 8 and 4 is 12, not 14, 12. So signal voltage, right, that's the lowest. So if it's 12, you just multiply by 12. So it's 30 millivolt. State two advantages of transmission of data in digital form rather than analog form. Memory work, signal can be regenerated or noise removed. Not non-noise, we remove the noise. Circuit more reliable. Circuit cheaper to reproduce because it can be mass produced, so it becomes cheaper. Multiplexing is possible. I can use different frequency carrier to carry the signal. Error correction. Right? You can check for error correction. Easier encryption or better security. An analog signal S1, as an analog signal, is converted into digital That's your digital signal. Using an analog to digital converter, after transmission, the digital signal, it is converted back to analog. That's your analog signal by your DAC. Using a digital to analog converter, outline the process by which the ADC convert the analog signal S1 into digital signal D. Okay? Sample the analog signal at regular interval and convert it to digital number. The ADC and the DAC operate with the same sampling rate and the same number of bits in each digital number. State the effect on transmitted analog signal ST when for ADC and DAC the sampling rate is increased. Smaller step depth. Oh, sorry. The number of bits in each digital number is increased. Smaller step height. So you can see most of the question they ask you quite similar question this part. This part can see they repeat. And this one is a June paper 42. Okay, so that's the end of the lecture. If you want to follow, you can go to Facebook, download this is a note, PowerPoint and the video. You want to pass your question on 2001 to 2010, topic by topic, to practice, try out. The answer is all there in your this one, physics, past year paper A2. Or you don't have a Facebook account, you can go to YouTube. Under my name, you can search for Digital Communication Part 2. Thank you. That's the end of the lecture.